Go on.
Okay, I can start.
Yes, please.
Okay, so hello dear colleagues. My name is Denis Bakhvalov. I'm from RF Software Department. And I really would like to welcome you to our next CodeDive community meeting. And today we will talk about C++ linker. But to start with, I really would like to thank you for all of you that you came here today in your free time and to know something about C++ linker. I really appreciate that you made your choice in this way. We use C++ linker every day, right? But mostly its work is often hidden from us. And we only remind ourselves about the existence of this tool when we see strange errors like unresolved symbol something something, right? But still, I think it will be good to learn and to know more about the traps we can get in while working with C++ linker. So we will cover some basic things about work of the linker. Although I'm almost sure that there will be a lot of interesting material even for those C++ developers who are really advanced in this topic. I prepared quite a big amount of information and material, so we will split this into two parts, and we have a little break when you can ask your questions or go for a cup of coffee. Yeah, and please be ready for some C++ code and diagrams. So, and let's start. And of course, the question is, what is linker for? What this tool is doing? To answer this question, let's start from compilation steps. Of course, I can assume that you all know about it, but just let's quickly go through just to remind ourselves about it. First stage is pre-processing stage. Second, translation, third is assembly. For us, the most important stage is linking. We will focus on that today. So, pre-processing. Well, this stage is really easy. On this stage, all preprocessor commands are like defined and include are expanded. So here you can see really simple macros that is also well known as unused variable. And as the first stage, in preprocessing stage, you can see the output using this command in G++ or GCC with -e and -p option. And as you can see, as the output, we receive these macros already expanded. So, but okay, here the first my tip will come right away. If you will include, for example, EOStream header file in your CPP file, this will drastically increase the amount of your object file in the very end. So please do not include everything in your CPP file. This might seem a little bit trivial, but I'm almost sure that you all know this. Okay. And the second stage is translation. On this stage, lexical analyzer analyzes your code for syntax, or just simply validate its syntax if it's correct. Also, your program is divided into tokens, and in the end, as the output, we will receive the assembler code for your C++ code. On this slide, you can see, for example, in the text segment, you can see the name of your function A. For example, this value 5, 6, 7, 8, and you can see in the that also there is data segment or data section. You can see this here, the name of your static variable and the value for it, right? So you can receive the translated, the assembler code for your program using -s option. This is translation stage. The third stage is assembling. On that stage, just simply your assembler code is transformed into machine code, just simply bytes. You cannot open. Okay, we can see the assembler output. Just it is simply listing. We can open it even in text editor, but we cannot open the result of assembling stage. But don't worry, we have special dedicated tools for it. For example, one of it is NM. This is for Linux. This tool is quite powerful, and we'll see today a lot of examples, and we will make our analysis using this NM tool. And here we can see this -c and -s option. But okay, maybe I will describe them a little bit later. To receive, to stop the compilation process at the assembling stage, you need to put -c option to the G++, and you will receive this object file for your CPP file. In this here you can see that we also can see the name of the function A and the name of the static variable. Okay, so far so good. Just let me introduce you one more tool. This is called objdump tool. Well, also this tool is quite powerful, but I just want to show you the output with the -s parameter. This tool is also showing the contents of your object file, but here -s option shows you the contents of all sections within your object file. Okay, so here we can also see the text segment, data segment, and we can see this 2e16 variable. It stands for 5, 6, 7. Sorry. Yeah, 1, 2, 3, 4 stands for this value because it is in data segment. Okay. Okay, and yeah, really, and because this is an assembler code, this 2e16 stands for this value 5, 6, 7, 8. You can try to convince yourself, or just believe me, this is true. Okay. Okay, assembling stage. Objdump output. Yeah, and if you want to learn more about this tool, or you want to see all its options and what it can do for you, what this tool can do for you, you can visit this link. Okay. So what next? I just want to remind you that only CPP files are compiling in C++ language. Header files are only included in CPP files, but they cannot be compiled standalone without, and they always included into some CPP files. And as we can see here, on the compilation stage, this is compilation stage, everything that is up from to this line. On the compilation stage, all the files, all CPP files, do not know nothing about each other. But well, still we need somehow to combine them. And this is the work for a linker. Linker just simply combines all object files into some binary, right? Okay, just let me show you one example. I will just write it on the board. Consider we have this function. This is really, right, really simple example. Well, this is absolutely valid C++, right? And this code is perfectly compiled. Besides one thing, this code is not linking, right? Why? Because we should have foo defined somewhere. Well, and if we will combine this object file with the object file where foo is defined, well, our work will be clear. Everything will be just perfect. Exactly like in this example. We have a CPP file where a function is defined. And we have main CPP file that uses this function. So, I just want to describe you the work of the linker from the other side. In simple words, linker tried to build some kind of a bridge between different object files. Like here, this arrow is some kind of a bridge. When we will combine two object file, for example, a.o and main.o, well, we will know where we should go if we want to where we should go in main in order to call the function a, because now we see all the picture. Okay. Yeah. Okay, so now just let's do a little bit of analysis and analyze this this really easy example using NM tool. Here we can see that inside main O there is a function, a special symbol A, but as you can see here, it has uppercase U class. This uppercase U class stands for unresolved. Okay, this is one point, and you can see here that in A.O, this A symbol stands for T, has class uppercase T, which stands for text. This means text segment. And in executable that was built from those two object files, we also have T. That means that the symbol is pretty defined. So we can say, in other words, that linker's work is to resolve. Sorry for this, but resolve all unresolved symbol, or resolve all undefined symbol. This is linker work. So I think that now for you it's no surprising, or it's pretty much clear why we should why we see those errors exactly from linker, like unresolved symbol something, right? And mainly I can say that linker was designed for mainly two reasons. First, the first reason is to have interoperability with such languages like COBOL and Fortran. And the second, in the time when linker was introduced, it wasn't so much amount of memory available. So for compiler, it will be really hard to keep a lot of meta information from all CPP files, or in that time C files, that was compiling at one time. That means just simply compiler will run out of memory. So that's why this additional stage was created, like linking. Okay, and just one more example of using NM tool. If you go on this link, you will find once again the complete specification for all these symbols like U, T, B, B, and D. But the common rule is that all uppercase letters are always used for the symbols that have external linkage. When lowercase letters are always used when linkers describe the symbols with internal linkage. Just let me not explain what it is. I hope that you all know what is external linkage and what is internal linkage. And symbols with no linkage, like this variable, is not even present here. For linker, it is not interesting. Linker do not care about symbols with no linkage, like variables that were created on the stack. So you can see here, the uppercase B stands for global symbols with external linkage. That's why here is uppercase B. Lower B stands for also global. Sorry, not global, but okay. Of course, this symbol is with with internal linkage and not initialized B. And this lowercase d stands for symbol with internal linkage and initialized. That's why it's D. And B means that the symbol is not initialized. Okay.
But we have still to remember that static is always initialized with the zeros.
Yeah, well, yeah, that's true. That's true. Thank you. Well, yeah, what you said is true. This B means that this symbol will go to a special segment called also BSS.BSS, and this means that uninitialized, and when our application will be loaded, all those symbols will be initialized with 0. Okay, so if it is clear, let's consider one example. I called it rules without enforcement. And okay, later you will understand why. This is really interesting example. So, as you can see here, we have almost the same two files, a.cpp and b.cpp. The only difference, okay, it has struct s that defines one method named foo, and all it's doing just simply prints a.cpp, and in case of b.cpp prints b.cpp. And that's the only difference. And inside a.cpp is function foo a, and inside b is function foo b. And in the main function we just simply invoke those functions. Okay, example is pretty clear, right? Okay, so now the question to you: what do you think will be the output of this program? So it will
Functions full A and full B won't be found, but then
why?
because you're not including any of those files. When you are linking this main file, you don't know where to take those full A and full B from.
Okay.
It would be the duplicated symbol of struct S.
So is this valid code?
Yes.
Is this absolutely valid C++ code or not? Okay, sorry, I will just answer first question, okay? So, for example, we have this here, okay? So, I will just simply rewrite you this code in the same manner. Okay, does this code compile? Just simply, what is the difference between this code and this? This code is completely equivalent because when on preprocessor stage, this instruction will be replaced by this, and this will be exactly the same. So here we have no error. Everything is fine. Linker do know where to get full A and full B.
What about the struct S?
Yeah. Right. This is the main question.
Types can be duplicated, but only if all the copies are the same. Otherwise, there would be no point in placing structures or classes in header files, which are included in multiple source files. And here we have same structure within the namespace. It's the same structure, which is not identical.
Linker doesn't process any types.
Yeah, so Linker has two choices. Either he can do whatever he wants, and it's your fault that you wrote the program badly, or if it's nice, it can try to check whether both definitions are the same and warn you that there's something wrong.
Okay, sorry, what means are the same?
I don't think Linker is that
And
smart.
from the Linker point of view, there is only a binary code, right?
Mm-hmm.
But it can check whether the binary code is the same as the other binary code. If they are not the same, for sure it's something not right.
The same you mean by exactly?
Binary the same, yeah.
Binary is the same, binary is the same.
Yeah.
Okay.
That's
okay. If
at
it's
least
not
he can
the
try to
same-
do that, but likely it's not required to. It's programmer's fault, and Linker it's likely not required to do anything.
Okay, we have an expert.
Yeah, I would say that linkers do not implement artificial intelligence. So
No, I
it is possible theoretically what you are saying, but I don't think there is an implementation in the world doing such advanced reasoning.
Well,
That's
okay,
quite
simply-
simple to check, actually.
Simply, you were almost right, really almost. Besides the fact that Linker simply doesn't care about whether this code is binary the same or not. Just simply. So okay, your answer was really good, really. Here we can see the answer, the right answer. What will be? So it looks like all the time this method is invoking, and this method is do not even exist.
Back to the answer. Actually,
Oh, sorry.
It depends on the order of linking, yes?
Yes, that's what I wanted to point. It's only part of answer.
Yeah, you are also right. Okay, yeah, it depends. It depends. We will see it
Might depend.
later a little bit.
It depends, I guess.
It depends, really. It depends. Okay, you are true. So okay. Actually, as you can see here, I just simply changed the order of providing those object files to the linker, and the result is this, as you said exactly. So now let's do an analysis for this using our favorite tools. Here you can see the output with -d option with obj dump tool. This is assembler code, but interesting thing is here is that we see the code for foo A and foo B, right? And we can spot that all those functions invoke the same calls, the same address or the same function. If we look at this function as this method foo for structure S, then we will see that simply it uses this address. This address stands for ACPP. If we will revert the order of linking, then we will see B. Here we will see B CPP and then ACPP. Sorry. Okay, now let's know what the C++ standards say regarding this. C++ standards say the following: there can be more than one definition of a class type with external linkage, exactly like we have. Given such an entity named D defined in more than one translation unit, then so here is important note. Each definition of D shall consist of the same sequence of tokens. And then, if the definition of D satisfies all these requirements, then the behavior is as if there was a single definition of D. If the definitions of D do not satisfy these requirements, then the behavior is undefined. So this is the answer. In our case, we break this rule. We for our structures, the sequence of tokens is not the same for those structures. For ACPP and BCPP. That's why it's up to linker how to do it. How linker will do. Okay, in this case, the answer depends on the order of linkage, but a different linker can implement a different way of how to handle those files. In which order? That's why, in general, in this case, behavior isn't defined. Unfortunately, like this. Okay, so we are going a little bit deeper, and now let's consider static libraries. Okay, I also almost sure that you all know what is static libraries, and you all use them quite a lot, but still. In simple words, static library is just a building block for many applications. So you can use static library in a lot of your applications, or provide it to somebody, and someone can also use this. As I said, this is just an archive or a collection of object files. Usually in Linux systems, this let's say traditional way of naming the libraries exist. Like you will have prefix lib and suffix and extension .a. In Windows, there is no special requirements besides that the extension is .lib. Okay. Yeah, so this is just as I said before. We have three libraries that can be linked into some other binary files, like some executable file or some shared library, which we will can consider a little bit later. In this example, you can see that lib A, lib B, and lib C are statically linked into a shared library, and lib A and lib B statically linked into executable. It just simply means that all code, all object files from lib A and lib B will be included into executable. So this is just really simple process, but not so simple, as we will see a little bit later. And you know, not so long time ago, I faced the problem. I faced the question: do linker throw away unused code? This is really interesting question. Was for me. Do linkers throw away unused code? What is your opinion?
No.
Yes.
I guess no, but you can enable this, but by default no. I guess,
Okay.
but I'm not sure.
Okay, so the next question: what is unused code? How we can define unused code?
Unlinked code, let's say.
Sorry?
Unlinked code which wasn't linked. And
Yeah.
But this interpretation might differ whether we are building shared library or executable.
yeah.
For shared library, pretty much anything which can be symbol, any symbol by default is public, so could be potentially used.
Okay.
Yes.
But the static library is the same. Well, okay. If we're talking about Linux, all symbol is public. Let's say exported from the library. Yeah.
All the code is used.
Yeah. All the code simply is exported. In shared, in static libraries, this is valid. All the code is exported. We can use any functions that this library provides us. It's true. So. Okay, and your answer was that linker do not throw away, or?
Yes, by default the linker do not throw away the code.
Okay. Any other opinions? I didn't say that this is not true.
Throw away if there are no references.
No references. Okay.
Well, my opinion is the same. I don't think linkers are that smart. I mean, maybe it is possible, but
So it is not
I
throw
think
away.
I would guess that in practice people do not want to use the time for developing this artificial intelligence feature.
There are
Yes,
many type of
but-
organizations.
Okay.
There are never
Okay, I get it. But let's consider we are, for example, we want to use some library from Boost. Boost is every Boost library. Almost every Boost library is really huge. We're compiling this Boost library as a static library, and we want to use it. Just imagine, for example, we want to use graph library, and we need just simply one short algorithm that calculates, for example, shortest power within the graph, shortest path, within the graph. But we don't need to use all the other algorithms and functions that this library provides us. And this will drastically increase our binary size in the end.
Yes, of course.
Right? So, but okay, we will know the answer just in a second. Yeah, and let's consider this example. We have a counter.h header file that consists just simply this is I'm almost sure that you know this strategy. This is counting the instances. This class is counting its own instances. It has a static member count which is initialized with 0, and simply in constructor we are increasing this static member. This code is really straightforward. And we have ACP file which only declares a static instance of this class. and we have BCPP, which also declares a static instance of class counter. And we have main CPP. All this main function is doing just simply print out the counter value. Okay, and let's try to compile and build this application. Well, the result is pretty much expected, right? We just simply have 2 instances already, so the result is really fine. But now let's ship those 2 object files. Sorry, not 2, but also 3. Let's ship AO, BO, and counter O not as simply object files, but we'll ship it as a static library. Whoa! And the answer is 0. So here comes a guess or a hypothesis that somehow we do not have those static instances, this instance A and instance B. Now we don't have it. So simply the reason of such behavior is that linker throw away or drops these unused object files only if they were originated from static library. Okay, and now what is this unused code? So the official definition for this is that starting from the translation unit where main is defined, every reference, exactly like you said, every referenced symbol causes object file not to be included. So simply, if this if the symbol is not referenced, it will be not included into the final binary file, but only if this file, if this symbol is originated from the static library, like in this example. But we can force linker to add object file. So simply, if we will add explicitly a.o, then we will leave linker no chance to not to include this object file. Okay. And as you can guess, if we will add here b.o, we will see 2. Oh, sorry. And there is a special option. That forces the linker to include all object files from static library. Really all. This is this option, but please be careful with this. First, as we discussed this example with Boost library, it can drastically increase your size of your final binary or final executable or shared library. And please do not forget to put this no whole archive option when you don't want to use this forcing way of linkage anymore. Yeah. So okay, this is pretty much all for first part. Now, if you have the questions, you can ask. Feel free to ask, of course, or you can just go for a cup of coffee, but please return back.
I have a question.
Yes. Sure.
Could you move back to the source of counter and A and B? Okay. We observe the same behavior of not throwing away unused code when counter B and counter A are not static. When you remove static, is this the behavior?
It will not implement.
No, actually, it's not infrared.
Static is only when you have an instance of one object, for example, structure, counter. When it's static, every running or actually explicitly saying I need static counter B, it will increase the counter. But when you don't do it as a static, it will be still the value what was initially.
But the constructor will be called, it's not static.
No,
the constructor is.
So, okay, you asking what's the difference between this if we will throw away static word?
Yeah.
Just simply, this is for sure still a global variable, right? Global variable, it means that this variable is global, and this variable lives all lifetime of your application, like static variable. The only difference is that here this symbol A will have internal linkage, not external. It means that you cannot reference this A object from, for example, from main.
Yes,
It is not global, but the result will be the same. Because it is still global variable. It will be global variable, and it will be also live all lifetime of your application.
Print will be different.
So even if the object is in internal linkage, it won't be removed if there are no references in the code.
Aha, you mean, okay, you mean, well, in general, this code still will be unreferenced, right? I mean, this A still will be unreferenced. That could lead us to the point that it will be also removed.
But
I guess.
also print will be different.
Definitions. You can remove unreferenced definitions from one object file if you use sections during compilation.
Okay, sorry, can you please repeat once
And
again?
you have a reference to a function in one source code, and you have a second function in the same source code. You can, which is not referenced, you can remove these definitions from the target binary too. If you use data sections and function sections in GCC and GC sections in linker, it will drop unreferenced symbols inside objects.
No.
Yes, because if you use, the problem is that during the compilation without data sections and function sections, without this, you won't have information about exact places, you won't have sections, well, the object file won't be divided into sections of text and data. And if you have these flags, you will have separate sections for each function and variable. So the linker will be able to drop unreferenced functions in the target binary, even if they are in an object file which have another reference.
Okay. Well, maybe I will say it in other words. Okay, just simply, the rule which linker use is the following: if inside object file there is no reference symbol, then this is a clear path to remove it from the binary. Okay.
If there is no reference at all.
Yeah, exactly. If there is a reference, then it will be included for sure. This object file will be included for sure. But if there is no reference inside any code inside object file is not referenced, it means that it will be removed.
Yeah.
But okay, we also should keep in mind that this is also only valid for static libraries. When you ship this code. Okay, and sorry.
If you go a little bit one slide before.
Okay. Oh, sorry.
Okay.
Is this behavior allowed by the standard? Because standard has no notion of shared libraries or static libraries, so for sure it doesn't define it in those terms. So does it define it in other terms, or is it just GCC optimization, which in this case turns out bad?
Yeah, this is actually a good question. I can say that I cannot provide you some information from C++ standard right now, as I unfortunately haven't found this information in C++ standard. Although this is a good question to investigate, really. Yeah, thanks for this question. Although maybe someone can answer this.
As far as I remember, there are translation units defined in C++ standard.
Yes.
Okay.
And it's allowed to do such
Yeah.
things.
That's all I remember too, so I was a bit surprised. I expected standard doesn't mention any such thing. So this would be, well, vendors optimization. Artificial intelligence which turned out to be artificial stupidity.
Okay, so we can have a break, 5 minutes, okay? If you... Thanks.
Go on.
Okay. So I think we can start the second part. And in the second part, we will mostly talk about shared libraries. Yeah, I also want to say some words about this name. In Windows, you will also face like the different name for the same thing, like dynamic library. It is also called dynamic library or DLL. So, in general, dynamic library is also used to build in your as a building block for your applications. But in comparison with static library, it has some advantages. First is memory savings. Simply, if we consider this example with libf.a library, this is static library. This is the example above this line where we ship this function printf. Imagine that we ship this as a static library. Sorry. And in this example, we will ship this printf function as a shared library. Also, you can see the naming, the way of naming those shared libraries. Also, prefix lib and extension so. Okay, I will talk about it a little bit later. Memory saving. Simply, it means that shared library is shared. The contents of this library or the printf function is shared between two different processes or two different applications. Thus allows us to have only one copy of this function, not really many, because here we will have a lot of copy of the same function. And well, we can imagine how many applications use this library, and well, it will be really not fair to lose such amount of space, even we should consider this is physical memory. Also, physical memory also, and the space on the disk. Second advantage is modularity. This advantage is not so straightforward, but also very important. It simply means that if we will change printf function, there's no need to recompile those two executables. We just simply need to recompile this library and just simply to restart those applications. And the new version of printf will be available for all the processes. And third is dynamic linking. This is also important advantage. We can manipulate when we want to load our printf function and where we want to unload it when we don't need it anymore. This is also we can imagine that we can have relatively small executable that will just simply load and unload some components in the time that it simply needs it, right? Yeah. So as we already touched this topic, from static library, all symbols are exported by default. This is also true for Linux shared libraries. In Linux, all symbols from shared library are exported automatically, while on Windows this is not the same. We should do this manually. We should export every symbol manually. Well, this is a little bit of constraint, right? But it was done in some optimization that took place maybe a long time ago. There are several ways to export symbol from shared library in Windows. But we will for simplicity, consider only this _ decal spec qualifier. I'm almost sure that you can find other ways on the web. It's really easy, and those options are also available to use. And, you can find it by yourself. It's no problem. Okay. But now I want to show you that I want to describe two ways of how we can link our library into your executable or your process. While in static library there is no way there is no choice. We can simply just need to specify what library you want to include in the compile time, right? But in the shared or dynamic libraries, it's not the same. We can have statically linking or dynamically linking. I will just want to show you first static linking of dynamic libraries. When we statically linking dynamic library, it means that we want to use this library during the whole lifetime of our executable. But on the other hand, this library will also be shared between many applications. And this is a schematic view of this process. In the compile time, so maybe it's not so clear to see, but here we have compile time. This is lifetime of executable, lifetime of shared library, and this is runtime. So first we are compiling and linking our shared library. Then we compiling our executable, and we specify the link between we specify the dependency from shared library for our executable. It means that just simply linker will look for imported symbol for symbols from shared library. The important note here is that symbols that found in shared library are not included into executable at the compile time. Why? Because simply we don't know even the addresses of those functions. Why? Because this library is not even loaded into the memory right now, and we should keep in mind that this library should be shared between many processes. That's why this stage is done on the runtime. Instead of the real addresses, only the names of the symbol are placed. When our executable is launched, operating system loads our shared library, and exactly in this point, only small version of linker is called, and this is the final stage of linking. When shared library is loaded into the memory, now we know the real addresses, the physical addresses of each symbol within this shared library that we want to use in our executable. Now we are free to we can put the real addresses in our code in executable. Is this clear? Okay, I hope so. Yeah. Okay, now I will show you the example of this statically linking. We have this main DL. We have some source file for our DLL. Sorry, I know that this may be a little bit confusing, but this DLL we also can we can assume that this is shared library, and the DLL is the same things. Only with this function do hello from main DLL. So this is the code for our shared library. Only this part, and this part is for part of code is for executable. This is how we can simply link statically our dynamic library. First, we are building our shared library with this minus shared parameter, and next in Linux, this is only for Linux valid, but we should just simply place here the name exactly like in static library. And also, please note this: we are changing this LD, this environment variable that has the name LD library path. This is the path where operating system looks for your shared libraries when it tries to load your library. And we are exporting this variable and run. And here is the example. Here is the result. I also would like to introduce a new tool that also will be, I hope, important for us. This tool is LDD. This tool shows all all statically linked, all statically dependencies of our executable. Here we can see that our executable, simple example, is dependent, has dependency from libshared lib.so, and this is the path. I hidden it because it's too big, and this is well, this is just simply the path to our library. Yeah, and just a small hint for you: if you see such error, like error while loading shared libraries, just first thing you should do is to check how you set your this environment variable LD library path, because simply this operating system cannot find your library. Okay. So this is, I guess, the example with statical linking is real easy. But let's consider dynamic linking. Well, it's also easy, but there are a little bit differences. As you can see here, on the compile time, there is no link between shared library and executable. Really, no link. On compilation time, they do not know nothing about each other. All dependencies are only visible in the code, if we look in the code. But dependency, of course, is on the runtime. We are manipulating loading and unloading the shared library from the code. Yeah, and also it is done like in here. The real addresses of symbols are put on exactly in this moment when library was loaded into the shared memory. Then we really know the real addresses, physical addresses. So here is the example, the same example, but difference, as you can see here, is extern C. Yeah, I also can assume that you all know what this extern C means, but simply in C++ there is such feature like name mangling or name decoration. Because of in plain C there was no such features like namespaces and function overloading, then there was simply no need to mangle, to decorate our names. But as far as many functions can have the same name but different parameters in C++, this solution for those features was introduced, name mangling. And with this extern C, we tell the compiler not to decorate those symbols. Just simply, in order that this function would be able to call from C code, or in this example, we should know the real name of the function. Because if it will be decorated, you will see just in this slide. Here we can just simply put the name of the function with no decoration, really. If this function will be decorated, then we will force to put something like here in the beginning and here in the end. But okay, how we can write a platform-independent code? Because different different compilers can decorate the function names in really different way, how it want.
So there is no standard for decoration?
Yeah, of course. There is no standard for decoration. It is really up to linker to, up to compiler how to decorate them. So let's go back to this example. You can see here I included this header file which defines this function, this and this. What we are doing, we just simply will with DL open. This is example. Okay, once again for Linux. In Windows, there are the same functions like load library. Load library that loads this library, and just simply as this. And we receive handle. With this handle, we receive the real pointer to the function, to this DLL main DLL function. And with this line, we are invoking our function, this main DLL, and closing and unloading our library. And this is how we can simply do this thing using G++. Okay, as you can see here, there is no dependency between executable and shared library. Really, no dependency. The only dependence is that we are linking statically this DL shared library that which has those functions defined: DL open, DL sim, and DL close. And once again, we should specify this parameter. We should set this variable.
One question.
Mm-hmm.
Can two different dynamic libraries export symbol or symbols of the same name? For example, a function of the same name.
Well, it's a good question.
Yes, they can.
I hope. I thought also they can. Why? Because simply we will have the different handles, and this will be different addresses.
Okay, but in this case it's clear. But in case of this dynamic linking, when you do not load, in the case when you do not load the library explicitly but implicitly by the loader.
Mm-hmm. You mean static linking?
Or what is the name? Static linking. Okay, whatever is the name.
Mm-hmm.
Okay, so it looks like in that case the symbols are referenced not only by the symbol name but also by the library name as well.
Mm-hmm.
Then it's possible to resolve the symbols correctly.
Okay, this is really a good point. Although I'm not sure that there will be no error on from linker.
From
code point of view, there is no solution to this because when calling the function, when using the static linking to dynamic libraries, you basically the compiler does the same thing behind your back. But from the source code point of view, it is as if all the functions placed in the library were just unresolved references that will be resolved in a fixed table. And well, when the functions have the same names, then there is no way to tell from which library it should be to resolve. Even in on the code point of view, if you ask a programmer, how would he tell which functions he means? There is no way to tell.
That's true.
He might have an opinion about what function he calls, but if asked to justify it, he will not be able to, because there is no distinction between these functions.
Well, you just get the definition.
That's a good point. Will we receive something like ambiguous symbol?
Or maybe the behavior is undefined.
Yeah, that's very likely. Good excuse is undefined and think I can.
There's something like import table in Windows dynamic libraries, and there is name of the dynamic library, and if, for example, there is kernel 32.al and have some function foo, and there is another library like user 32.al and has also function foo, then linker actually knows which should be loaded.
How he knows it? If you call then if you have in source code, if you have just foo and parentheses, then how he knows which foo you meant?
Exactly, that's the point. In object files, you have only the names of the symbols, and you have no information about the expected libraries.
Okay, exactly.
I have noticed about this example because we are losing type safety.
Yeah, okay. You can also say that we are not checking this handle.
Yeah.
For whether it is valid or not. Yeah, this is true, but this is just an example.
To know what we are allowing.
Yeah. So okay.
Also, we are moving the. I'm just noticing that there are some. Features to remember.
Okay, so this is a good point. Thank you. That's true. Okay. Okay. So now, just to a little bit make it more complicated, let's consider one example. This example is, well, also from my own experience, and I can say that I do spend quite a lot of time on fixing this. So we have counter h, the same structure, the simply struct or class. Let me call it class, which just simply counts its own instances. But we have here static method that here we have static variable and just simply increasing it all the time, right? And we have shared library. We include this counter, and in the main function of our shared library, we just simply create an instance and printing the address of this counter. This is first of this of static counter of this counter. Yep. And we are printing its value. So far seems very simple. Here is our executable. This is executable. We have main CPP file. Also include our counter. We are defining our function from DLL from shared library, and in main do the same thing, like invoking DLL function and do the same. Also printing the address of the static member and printing its value. Okay, so let's build it and launch on Linux. So this is how we're doing. Yeah, and I forgot to mention that we are statically linking our shared library, statically linking to our executable. Yeah, this is the whole process, and we can see that this is the same counter is addressed. Well, really what we want, right? Pretty much expected. This is exactly what we want. We also should keep in mind that okay, in symbol are all symbols are exported automatically, right? But let's do a little bit of analysis once more using our NM tool. We see that for this counter in a shared library we have symbol V. According to description, this is a weak symbol, and also we can see that in executable this counter is also a weak symbol. And according to description, when a weak undefined symbol is linked and the symbol is not defined, the value of the weak symbol becomes 0 with no error. It means that it's up to linker to choose one of these two symbols from shared library or from executable, and it will resolve it with no error. But let's just go back, and we can see this address. We can see this address, and this is this address is this. So we can say that in this example, linker choose let's say our own as we are compiling our executable. Linker choose our own counter, and just simply ignore the one from shared library. Well, this is really expected, nothing strange. But let's move forward and let's run the same example on Windows. In Windows, we should export all symbols automatically. Sorry, manually. So we should do the following changes. We should declare this function main DLL as export, as __ decal spec export, and in executable we will import this function using __ decal spec DLL import. On Windows this process is really complicated, and let's see how we can build it. To make this, we should use this option. As far as symbols are not exported from the shared library itself, but we can export it, and this command will put this symbol main DLL in special let's say export library that will have this name. What we are doing is creating this import or export library. For executable, it will be imported. That's why it is import library, and we are generating this export file, but it has the same name as static library. At least it seems like this. And we are putting as an input this statically library, this export library to the executable.
This is how Redmond complicates simple things.
Yeah, okay. And as you can see here, I launched this, and I can see that there are different counters. Those counters are different, and the values are the same. Two different counters. Okay.
Can we get back to the Linux example? Doesn't that mean that if the linker chose the executable version of the variable, doesn't that mean that if some other executable linked to the same library, they both run at once, we will not see a tree, but we will see instead two twos. Because if both executables choose their own version of the counter, then we will have two counters, while one would expect that the counter should be within the library.
But why? But why we should expect why we should expect the same value in shared library? I guess operating system will not like this our way of communication between the processes. No? So look, right? It's on address space. We cannot modify the shared
but the shared library is within address space of both processes. We do not talk what it's nice to program, but what it's possible to program, right? If the shared library is in address space of both running processes, then both have access to it.
Sorry. We will have an access to the code, to the text segment, but we will not have the access to the data segment.
The data is the different business.
Yeah, exactly. The data is different business. Okay. Simply, when the shared library will be loaded, the data segment from, as I already heard the word relocated, the data segment from shared library will be relocated to the address space of executable. But if we, if another executable will also launch, those two executable will not address the same counter.
So that data part of a shared library is duplicated for every running.
Exactly.
Yeah. So in this case, obviously, you do not expect to see it.
Yeah. But
in Windows they play with it somehow. That I think you can share objects somehow inside or from inside one library between processes.
Yeah, that's why I asked the question. Because in Windows you could
generally, I read that by default it works like this.
But there is a way that you can.
So maybe you will know better than me about it.
Because I haven't played with Windows for years, but I remember that there is such possibility.
Okay. Yeah, maybe it's true. So okay, let's process with the example in Windows, right? We have the unexpected behavior from our point of view. So let's do something with this. Yeah, we have two different two different counters. Whoa. And we can see in both shared libraries and executable. We have D class for our counters. D class stands for simply defined data, simply initialized data, and we have different addresses. If we go back, we will spot the same addresses here. Yeah. Oh, okay. Yeah. Also, I put this note. There is a little bit complicated way to prove that exactly those pointers, those values are using disassembled code as we do for the example in the first part when we are analyzing assembly code. You remember maybe. But simply, I will not do this. If you want to do this, you can do it manually. In the end of this presentation, I will provide you the link with all these examples when you can download this from GitHub, from a GitHub account, and run it by yourself and try to play with those examples if you are really interested to analyze it deeper. Yeah, but I created this picture just for you to better understand this, just to better understand what is going on. So, as we already discussed, this data segment was relocated here, and this means that this is a Windows version, right? And in executable, we have on counter that was on counter from executable point of view. It's our counter that is referenced from main function. As we know it from here, from this picture, we understand this that from main function, this our own counter is addressed, and from main DLL, this counter that was relocated from this segment is addressed. So we don't want to see two counters, right? We really don't want. This is the desired, our desired result. We want to have only one counter and address it from both main and main DLL. Or please consider this the same picture, but this picture, I hope, will help you to understand where from where this counter came from. So, just to remind you that both shared library and executable were built separated, right? So we have in executable, for sure we have our own counter because we include this counter hash now and executable know about existence of this counter, so it forced to create this counter because simply we will use this. And also, when shared library was created, it was also a need for a shared library to have its own counter. So the only way to process here, to process further, is to break this link. The idea to fix it is to break the link between this counter and executable. Simply, we should hide this static member from executable in order that it will be not created here, and export this symbol from DLL, from shared library. So this is a little bit long path, but still this is the way how to process here. And of course I will show you the code for this. Is the idea clear so far? Okay, maybe in when we will analyze this using an NM and object dump tool, it will be clear for you, I hope. So to fix this, first we are doing. Okay, you all, I guess, all know this way how to export and import the symbol using the same header, header file. We define such macros, export import, which in DLL will expand like decal spec underscore decal spec DLL export, and of course in executable it will be expanded as import. So with this approach we are splitting declaration and definition of counter. So here is the declaration, here is definition. We split it in order to hide this counter from executable. Right? We are exporting this structure and exporting all its symbols. So this is the first step. Second step, we are doing the same thing with. We are also exporting our main DLL function, and in executable we are importing, as you can see here. We are importing this main DLL function, and also this macros is defined before counter H. It means that this macros will expand as import. This is pretty straightforward. And we got it. We now can see here that we have the same, only one counter addressed. Okay, so we fixed this problem, but let's look at the analysis. Sorry. Okay, maybe there is no analysis. Yeah, but just like I said. So now we have this picture. Simply, it means that if we run this nm on our Windows example, fixed Windows example, we will see that here we have weak symbols that linker will only choose one from it, and here it will work fine. As we can see here, please remember this address. We will see it later. Yeah. So okay, maybe not a little bit exactly the same, but this address, that means that it came from the shared library data segment. Okay, but okay, we described how to reach the same and different counters in Windows. But let's also see how we can if we want so, how we can make that counters will be different for Linux also. We want to make this bug, and the way that I found, the only way that I found is to make different counters is just simply to implement this hack, is to simply redefine the name of the class. For sure, with this approach, we will force linker to create different counters, because there is even different classes. So we cannot count instances of different classes, right? So yeah, I can agree that this is a hack. Although I'm really for now do not aware of any other way how to do such a hack, such behavior. But also, please consider that in general there is more elegant way, and actually, really, what I just showed you, this example is maybe okay. It's from my own practice, but generally the bug lies not in maybe the root cause lies not in that not in the fact that we forgot to export also counter from shared library, and we forgot to break the link between header file and executable. This is strange, right? The problem has more elegant solution, and this is stated here. Simply, the much more safer and nicer way to do this is to transform shared library into static library. Simply with this approach, we will have something like this. If we will, imagine this is counter H. This is our not more shared, but now it's static library. And within this library, here is somewhere counter.cpp, and here we have our executable. And if we will include this file, in order we will know that, in order we will satisfy the compiler, and we will link statically this library, then the problem will never come up. Simply because actually this is the same picture as we received when we exported this counter from this shared library, but simply the much more elegant way is not to deal with those export manually, but the much more safer way is to transform shared library into static. But also I should say that it is not always always reachable, because, for example, in my case, shared library was so big that I simply cannot split it and or to transform it into static library, because it was too big, and this was the main problem in my case. Yeah. Okay. Okay. And in conclusion of this topic, just please let me show you maybe my way of working. Let's say my preferable project structure when I'm writing my own projects, but okay, we should talk about small tools, like small tools or small projects. I usually create the main functionality within some core that I usually make a static library. I created separate unit tests. Unit tests I'm usually implemented in executable or some dynamic library, because, for example, in case of if we will use, for example, the framework from Microsoft Visual Studio, there your unit tests will be implemented in like a dynamic library, not executable. But, for example, if you're using Google Test, you will in the end your unit test will look like executable. And simply I'm creating this another project that I usually name launcher, and this is of course executable, and I statically link my core, my library into the launcher. Why? This approach, in my opinion, has one important benefit, is that I simply can cut this part core, and I can put unit test cut and move it to any projects I want. I simply can quickly receive functionality in different projects that I need. Yeah, that's it. Okay, so here we are coming to an end, and I would like to say that all sources for all examples that we have covered today you can find under this link. But if you are interested in this topic, and if you want to learn more, I can just provide you those. I would like to encourage you to visit those links that I also visited when I prepared this presentation. Yeah, also you may find this very interesting. There are a lot of information there, and a lot of links to other resources. Yeah, and that's it. I would like to thank you very much for your time.
And can we get back again to this two counters on Linux?
Sure. Two counters, okay.
So it was one counter,
Okay.
On Linux.
Okay.
At the end.
Mm-hmm.
No, in Linux one counter.
Mm-hmm.
Sorry. So at the end of the day, we have actually two objects, but only one of them is referenced, right? In runtime.
Yeah, exactly. Yeah, exactly.
And for some reason,
Okay.
let's say during loading the library, the loader chooses or picks up one of the symbols to be used in resolving the symbol of that name. And it prefers the symbol from what? From the executable or from shell?
So in this example, this symbol, let's say its own symbol. I mean from the executable point of view.
Okay. So even the code in the shell library, it also references the symbol which comes from the executable. Right? Am I right?
Sorry, once again.
If you go to the previous or next slide, here. So we have both the DOL and exe referencing to the same pointer, right? Which means that the code in the library, after loading and resolving all the symbols, it references to the object coming from the executable. Right.
It's actually not from the executable, but executable probably refers to memory, where the shared library is.
Sorry.
Because you use shared library. Executable, how knows where the symbol for counter is for this library, for the shared library. It's the simple example refers to shared library counter address.
But this is not referenced.
No, in simple example, when in runtime you run the application, it tries to find the shared library.
Why you are talking that it tries to find the symbol from shared library? It is using this symbol.
Address. It's using address.
Here.
Yes. But okay.
Maybe I don't understand.
When you run the application, application runtime search or try to find the shared library which should be used, and also addresses for the symbols. Where are they placed in the memory?
Yes. Okay.
And this is address for the counter in the memory. Where the shared library is actually now in the memory, or you have shared library in your memory.
Okay.
When you run the simple example reference to that shared library somewhere in the memory, and this address is for the place for the counter in that. Loaded to the memory shared library.
I think it's the other way around. Somehow magically the code from with. Can you go to the previous slide?
When you run the executable.
Yes.
If you go a little bit more previous slides where you have timelines of the compilation and the runtime of libraries.
Timelines, okay.
You have here where he finds looks for the symbols.
Okay.
And here during the compilation he knows where the library is in the memory, or
here no, of course no. Because shared library is not loaded into the memory, right?
Okay, so here. He, in the compilation time, he somehow puts the address of the symbol of the counter. and you now in the NM application knows the address inside the executable. Or when you use NM, it actually runs the simple example executable and then loads the library from the memory.
No, we don't do so, as you said.
Okay, so,
it is not
so during this stage, he somehow puts the address of the counter, of the symbol counter. How NM knows what address is in the simple example executable for the counter?
Well, this is a good question, but how NM knows the address
of the symbol counter?
But
here, if you go back, yes, here.
So simply, this is simply from this binary, from simple example binary, right?
Okay, so where it's come from? When you have address in the
but this symbol is weak. It means that is weak. It means that linker can choose one of those two symbols as stated here. The value of each symbol becomes 0 with no error. This linker, this symbol is not defined, but yeah.
But here you've got linked executable.
Yes, but you have two symbols. You have one symbol in executable and you have the other symbol in shared library. So the output from NM on simple example only shows you the symbol which is defined in simple
Can you show
example.
the source code? And the source code of counter.h. Yeah, that's the point. That we have this counter which have actually defined both in shared library and in the
Yeah, of course, because it's
two symbols or two objects. And during this stage of let's say loading the library and starting the executable, the dynamic linker chooses one of them.
Yes, exactly.
And then shows definitions, place of definitions, as I guess. Place of definitions inside those files. Which file?
Not the memory.
There aren't just symbols, but NM shows what they indicate to. Definition.
A name just simply shows the address, the offset from the binary, from the beginning of the binary,
This is
and the size.
part of code with definition.
Yeah.
And as I guess, when we got both symbols inside definitions of this function inside executable and dynamic library, so compiler or linker puts information that it can found also this definition inside the library. So he knows he might got information about two places, but he chooses this from executable.
Your question is why?
Okay.
Or not?
Or does it?
This is just how does it work, and as I think.
Because,
I'm
as you
asking
said
just
before,
is it true?
as it said before, static library is loaded when we run the program, and we don't run the program when we running nm on the executable. So it sees only those symbols defined in the executable and not those in shared library. So it doesn't make any choices because it's only one symbol then. You get the other symbol when you load the library, and then you do the linking, and then the linker choose which symbol to use.
Okay, exactly. We can even prove this, right? Because this is just the output. We can see. This is well, for sure we can say that the same counter was addressed from here and from here, from main DLL and main simple.
I have a question about static linking of shared library. Is it possible, this is about safety issue, is it possible to inject some kind of code by yourself, knowing that not only this is, as we pointed out, this is undefined behavior if you have